for this afternoon. The first speaker, which is Ilaria Gianani from the University of Roma, who will speak about the spectral characterization of bifocal states.
Thank you for the introduction, and this is off. Okay. Thank you for the introduction, and thank you for the invitation. So today I'm going to show you some recent results we got on spectral characterization, which, as you know, is a theme which is dear also to the ultra-fast classical community, but here we will exploit it in the quantum domain. So just to set the scene, we consider we have a SPDC source where you produce your photon pair, and as you know, this has to abide to momentum conservation and to energy conservation, and these conservation laws can make it so that you have correlation, which can be position, in momentum, and or in frequency and in time. So if you want to look at spectral correlation, this can be helpful for many different applications, say spectroscopy, communication. But before you can actually use them, you need to be able to characterize them, of course. So if we look at the spectral domain, we can describe our state as, this is the point. We can describe the state as you see here, where this is your probability amplitude, which is given by the product of two functions. These are basically just the field, the electric field of the pump that you use for creating your single photons, and the phase matching of the crystal, the nonlinear crystal that you use for your SPDC. The product of these two functions is what is usually called the joint spectral amplitude. And the joint spectral amplitude is nothing more than a two-dimensional electric field. You can see it in this way, where you have, sorry for the an amplitude, which is usually referred to the joint spectral intensity, so the square root of the joint spectral intensity, but you also have a joint spectral phase. So usually when we talk about frequency correlation, this is what we look at, the spectral intensity, which can be uncorrelated or correlated. Here you have the axis are the frequency of your signal and your photons. And usually that's what people refer to when they talk about frequency correlation. And you can measure the joint spectral intensity, I would say easily, but with very long measurement, but very, say, routine long measurement. It's not easy, but it's done. Simply by mapping the frequency either in position or time. So either you use a normal spectrometer where you have a diffraction grating, or you can have some very dispersive elements so that your frequency arrive at different time on your detector, and so you can measure your JSI in this way. But then there is also the phase. And the point is that you can have spectral correlation also in the joint spectral phase. A very trivial scenario is where you consider the pump pumping your SPDC crystal. If the pump is transform limited, so if it has a flat phase, then your joint spectral phase can be as well flat. But if your pump is only chirped, so you have a second order phase to your pump, then you get correlations in your joint spectral phase. So your photons will exhibit frequency correlation, even if, for instance, the intensity is uncorrelated. Now, the point is, how do we measure the joint spectral phase? Because amplitude is, say, the intensity is, say, quite easy. The phase is where the problems are. And this is also true in the classical domain. You don't have to go up to the quantum domain to face this challenge. And basically, I will today show you two different main roads. One is to rely on the 4th year of experiments that you have and experience that you have from the classical domain and try to adapt those techniques to the quantum regime. And the other is to follow a more directly, say, tailored for quantum states approach. And we will start from this because it's our most recent results. And when I say most recent, I mean 2 days ago. So very soon. So this is actually the technique I will introduce is based on simulated emission tomography. Because you can see that if you have your SPDC source, or if you have the same apparatus, but you're seeding the measurement, so you have a simulated emission or different frequency generation, the matrix describing these two processes is the same. So as I told you, when you have single photons, this is hard to measure. I mean, the intensity part is long, so you need to have, you have low counts, so it's still more complicated than if you have laser beams, okay? And the phase-sensitive measurements, as I was saying, you can adapt techniques, and we'll see this later in the talk. You can adapt techniques from the classical domain, but usually these use nonlinear interaction to make the measurement. So it creates more problems. I mean, you can solve them, of course, but it's another thing to add to the tail. While if you look at this other scenario, where you have your pump laser and a seed that is seeding this stimulated signal that you get out, then these beams are, very laser beam, maybe very faint, but still you have signals, so you can use normal spectrometers to measure the intensity part. And then you can use stimulated emission tomography by changing the phase, controlling and changing the phase of your seed. You can extract information on the phase of your joint spectral phase, basically. And what do you extract of this information? You extract it up to a global phase, and you extract it up to a local phase on the stimulated signal, because you are only measuring the intensity of the stimulated signal while you're measuring the phase and amplitude of this. So suppose I add a dispersion here, of course I cannot take that into account. So whatever I reconstruct will be up to whatever phase I can then add on the stimulated signal. But in the end, so what you can retrieve are the correlations, which is what you care about. So it's all good. The point is, how many seeds do we need to do this measurement? And that's where we worked with Luis Lorenzo Sanchez Soto and Yongxia Teo. Luis is in Complutense Madrid. Yongxia was also in Complutense now in Singapore, about using a compressive tomography method applied to the skin. So they gave us a very clear recipe. What we needed to do was generate random seeds and measuring the intensity and phase of our seeds. For each of the seeds, measuring the resulting stimulated signal. And then there was this convex optimization algorithm with which we could check that this set was actually complete and the solution we are getting is unique. And then check that the JSA that we got has a fidelity that matches the molecular mesh method, so that we know that we are doing a good reconstruction. So they did some simulation, everything in theory is working very well. So, okay, we said, let's build the experiment. We come here with our TISAC laser. We take a pick-off that we send on a 4F line, which is where we shape our seed. So this part is our seed that then ends up on our crystal. And we can shape it to create these random seeds that we need both in amplitude and in phase. And the rest of the laser is doubled here by a CGG, and then acts as the pump of our SPC source. Then, as I said, we measure phase and the intensity of the seed and only the intensity of the stimulated signal. So this is our 4F line. Since we needed random phases and intensity, we actually decided that the most practical way was to put literally a screw in the middle, not in the Fourier plane, because we want to add the random phases. So we want this to be as messy as possible, literally. And so you see here that we recorded around a bunch of seeds. These are the intensity. For each of the seeds, we measured the intensity of the stimulated signal respective to that seed. And then we sent each of these seeds to a frog apparatus to measure the phase. So for each seed, we retrieved the frog trace, recovered it, this is the error, and reconstructed the spectral phase of each of the seeds. This is the temporal. This is an example of one of the seeds I showed you before, just so you have an idea of what happens. So we have all the elements to plug into this compressive algorithm, because we have the seeds, intensity phase, we have the stimulated intensity. Nothing worked. And we were a bit at a loss, because, of course, the first thing is maybe the seeds that we use are not random enough. Maybe they are not enough seeds, like literally they're not enough, or maybe we reconstructed the phase not correctly. Everything could have happened, But then we realized that there are actually a couple of technicalities, which are quite technical details, but they are quite important here. And I spoiled them for you now, then I will still show you in the simulation. But the problem was that our simulated signal, that are our probabilities, cannot be normalized to 1, which is what you usually do when you compress tomography. The reason being that the relative weights of this stimulated signal is important, because it ultimately leads to the shape of your JSA. So we had to keep the information about this relative weight in the algorithm, which is something that they don't know. And actually related to this, there is the problem that the way that they usually manage to treat noise with this algorithm relates to the fact that you can normalize everything to one, and we couldn't. So basically, this technique for us was completely useless with noise. It couldn't, even the tiniest amount of noise could not be accounted for. And as you know, that's a problem. You know, everything you do experimentally has at least some noise, so we were a bit at a loss. But we found a way to actually treat noise even in this scenario. It's a very technical debate, so I won't bother you with it, but we can now account it with the price to pay that you have to have at least an informed idea of how much noise your system has. So you have to have at least a ballpark number of the percentage of noise that you have to add and so on. So, but since this was the situation, this one, and nothing was working, we said, okay, let's go back to the simulation for a second, but let's do simulation informed from the measurement. So we take the measured seeds, so that at least we know that with this seed it should or shouldn't work. And then we use a JSA model, which is the one that we suspect to have at least. And from these, we retrieve the stimulated signal. So we simulate the stimulated signal starting from the measured seeds and the model we want to retrieve. Okay. So at least in this way, we decouple the problem. If this works, these are okay. At least we have a solution. And it did. So this is the target. This is the target intensity and the target phase. In this case, it's flat. I'll show you in a second one where it is not. So this is our JSA that we want to reach. This is the retrieve one. This you can see that it matches perfectly. What you see here is that, and I left it on purpose so that I will show you, is that here you have a phase that is varying only on this axis, which is the stimulated one. And as I said, we can retrieve the phase up to a local phase of one of the two components, and that's exactly what you see here. So these we can remove. So it only depends on this axis. It doesn't depend on this one, right? So we know that that was the case. And then we see that if you look at the fidelity, it goes to 1 once you use all your seeds that we measured. And if you look at this parameter that we use to say if the algorithm is converging to a unique solution or not, it goes down, but it doesn't go to 0. Exactly, it goes to something like 0.2, but that is to be expected exactly for the reason I told you, because we have ambiguities in the phase. We knew that already, so we are not expecting that you have only one unique solution that matches your data. You have a set of them, but they're all equivalent for your instances and purposes in the end. Okay, so this is the case where you have a flat phase, then we go to a quadratic phase. Here I have removed already the local phase so that you can see that these two matches, otherwise you couldn't see it if it was adding that as well. And you see that the reconstruction is done well, and this goes to 1, this again lowers, and everything works without noise. Then, as I said, we also have to take into account the noise. And the results you see here are with 10% noise on the stimulated signal, the stimulated signal. Sorry for the alliteration. And you see that, of course, things go a bit worse. We reconstruct it with a fidelity of 93%. This phase is mostly flat as it should be. You have some noise, but you do have that in the data, so it's okay. The thing that is a bit worrying is that this goes lowers, but that still it's a very high number. And the reason is because actually you are adding space in the set space that you arrive to, because all the different noise configuration are still viable for you. So you're not unique even more than just when you have the phase ambiguities. So you say, so how do I know that my reconstruction is good or not? Surely the fidelity is an indicator, but what you can do is you can compare your stimulated signal that you use, whether that is simulated or the data as we will show, as I will show you soon, with those that you retrieve from the model that you actually have gotten. If they are equal, then you know that for all your instances and purposes, the model that you recovered is behaving as it should, so you're okay with it. And then, okay, we went back to the data with all this correction I said. This is the target, and this is what we get. The fidelity is up to 95-something%, so we were okay with it. Again, the phase we were expecting to have a flat one, so it sort of is. Again, this doesn't go very low, but this is, as I said, I think this is still work in progress. As I said, this last couple of days work, but That makes sense, at least for now. I wouldn't give you a definite answer, but sounds promising in a sense. And so this is what concerns what I call the most directly quantum approach. But then there is all the rest coming from the ultra-fast domain, classical ultra-fast scenario that we can look at if this is not your this was not your cup of tea. You have other possibilities if you want to reconstruct the phase. So basically, if you look at ultra-fast metrology, arguably the two most used techniques are frog and spider. So frog is basically an autocorrelator method where you are measuring the spectrum of your autocorrelated converted signal in function of the delay between the two copies of your pulse. And spider, we will see it a bit more in a second, but it's, for now, just, it's an interferometric approach. And these two are basically interchangeable. I mean, I shouldn't say it being on Ian Walmsley school, but you can use one or the other depending on what you actually have on your table that you need to measure. I also wanted to mention this one, which is basically, it's called MICE, it's mutual interferometric characterization of electric field, which is nothing more than an extension of spider in a multi-shear regime. And I mention it here, and I'll show you in a second why, because the characteristic of this technique is that, one good one is that you can retrieve two fields without knowing anything prior to these two fields. So it's not self-referenced, but you don't need, it's not even a blind method. You can actually reconstruct the two of them together. But the important thing for what concerns going to quantum is that it has the most incredible resilience to noise you can think of. It's really, really resilient. And this resilience comes from the redundancy of how many measurements you have to do. I mean, somehow you always have to pay for these sort of things, and you pay in doing a lot of measurements, but such is life. Okay, so I think here the point is, depending, so these all have been adapted to the quantum domain, and mind you, it's not literally a technical adaptation. Usually it requires a bit more changes than you think of. And which one you want to use, I think, really depends on how your system behaves. So if you have a very stable system, because the main problem going quantum is usually that you have low signal to noise ratios when you're doing frequency resolved measurements. So if you have a very stable system, then you can live there measuring for the longest time, then either one of these may be the way to go. If you have a very unstable system, then maybe something that is more resilient to noise is the way forward. But even if you have a long possibility of making long measurements, and of course, every complication you add to the setup is bad, even classically. So that amplifies, I think, in the quantum. So the most simple setup you can use, the better. And along those lines, I wanted to show you this result we got regarding spider. We actually got it for a classical pulse, but I think it really applies here. And the idea is that by using, you have a normal spider setup, which I will show you in a second, of course. But the idea is that if you reconstruct the interferogram, your phase from the interferogram using a machine learning model instead of the normal spider reconstruction, you make it so that you can remove the calibration step in spider, which is annoying because in reality, and I'll show you, when you do a spider measurement, you have to take two measurements. You have to take a calibration measurement and then your spider interferogram. And that changes, so that means that your setup is not static. You have to make adjustments while you measure. And if you're doing this in the quantum domain, it's worse because you have to realign everything, and it's not easy. It's even worse than in classical scenario. So the way a spider, normal, the most vanilla possible spider you have works is that you have your pulse you want to reconstruct, you make a copy of it and you delay it in time, and then you make a third copy which you cheer, so that each of your test pulses sees a different monochromatic slice of this ancillary pulse. That means that when you send them on a nonlinear crystal, each of these two pulses will convert with a different frequency, generating a shear in frequency in the converted signal. So here you will have two pulses which are identical, but delayed in time and sheared in frequency. And you measure this interferogram, which looks like this. And what you care about is the oscillating term, which depends on this phase, which is called the spider phase, which is the difference of the phase that you want to estimate, the same phase evaluated at a shear distance, and then the carrier term, which is omega tau. Now, these first two bits are the derivative, basically, of your phase. So if you can remove these, then you can estimate your spectral phase. But you have to remove this. So in order to remove this, you can perform a measurement where you put the shear to 0. So these two terms cancels out. This is equal to your carrier, and then you evaluate tau, and you remove it. And then you're left with your spectral phase, which you usually can write as a Taylor expansion. And if you do so, then you're interested usually in measuring the second and the third order, so the group delay dispersion and the third order dispersion. But the crucial thing here is that you're using only the information contained in the oscillating term. So you don't care about how your interferogram actually is, because you're only extracting the phase. If you want to do the machine learning techniques, then, and you want to use the whole interferogram information, then you need to model the interferogram a little bit better, because in reality, your two pulses may not have the same intensity, for instance. You may not be centered around the ancilla, so the shear will be maybe added not equally to the two pulses, and your fringes will have a visibility, okay, which may not be one, which is never one, of course. So you need to take also these parameters into account, but if you use this machine learning approach, you can retrieve all these 6 parameters just from this measurement, and that is the key. You have more parameters, but you actually don't care. You just need to take them into account, because otherwise it won't work. So the way we went forward with it is that, so you have a cascaded neural network systems. All these neural networks, there are 4 of them here, have the same structures, which is a bunch of convolutional layers and then a bunch of dense layers. And the trick is that you basically start with all your parameters, the 6 parameters I show you, varying in a range that you decide, which makes sense for what you have. And then step by step, you start by estimating some of these parameters. And then you create a new training set, where the parameters you haven't estimated still vary as before. But the one that you have estimated now vary in the error that you have estimated on the previous network. Okay? If you do that, you arrive at the end where you have estimated all your parameters. And what I'm showing here is for the 3 parameters that you care about, so time delay, GDD, and third order, what you expect versus what you get, and you see that you are perfectly retrieving them for different values. And what you see down in here is the comparison of some data from Spider, analyzed with the standard Spider routine or with this neural network, and you see that these are the spectral phases, and they're pretty much equal. And this is the temporal reconstruction, and again, it's pretty equal. So without doing the calibration step, you could retrieve the same result. And this is helpful if you want to have, for instance, we actually suppose it initially classical, if you want to have a Spider system embedded in a laser for checking how the laser is behaving, then it's better to have a static setup than one with the calibration, for instance. But even if you want to go quantum, it's obviously better to have a static system setup there as well. So this is one way. How much do we have? 5 minutes, okay. Just the last thing, which is the quantum mice part. And as I was saying, this is nice because it is very resilient to noise. Briefly, how it works is you have 2 fields which can have how many dimensions you want, okay? And you interfere them by adding a shear on each dimension this pulse is made of. So if it's an electric field, you have just the shearing frequency. If it's a 2-dimensional field, you have to have shears in all dimensions. And you record an interferogram for each of these dimensions, or for each of these shears, sorry. So one of the interferograms will look like this. You extract the interferometric product, so the oscillating term, which is also called the AC band usually. And then you create this least square function with 2 trial fields, and you try to minimize this error. And from this minimization, you can retrieve both fields, and so retrieve both phases at the same time. If you want to transport this to quantum, you need to find a measurement of an interference of 2 quantum fields that look like this. Okay. And a way to do it is using a modified Franzen interferometer or a hub interferometer, which is what Paolo mentioned in his talk a couple of hours ago. And the way it works is that you have your source here, your signal analyzer photons, and they can either take a short path or a long path. But If they both take a short path, they will arrive on each detector, and so you will see a coincidence. If they both take the long path, they will arrive on each detector and see a coincidence. But if one takes the short and the other takes the long, they will arrive on the same detector, and so there are no coincidences there. So you're left with this state where you have the superposition of short and long path. So if we now introduce the shear here and here in a way which usually is electro-optical modulation, but anyway, and then we measure the state as a function of frequency, do frequency resolved measurements, then the probability of measuring a photon with frequency A and frequency B is actually of this form, where this is the long or short, and this is the short part. So basically, this is your biphoton state. This is the same biphoton state transport, but you don't care. It just needs to be there for it to work. You want to reconstruct this. And this looks exactly like a mice interferogram. So actually, we still have to do the experiment on this. We only had the simulation done and published a while back. Maybe this is the year we do it, I'm still not sure. And the idea is we start, so I'll show you the simulation very quickly. We start with this is our state, and it's an uncorrelated JSI with a correlated phase. We did H shear for each axis. So that means doing 64 interferograms, which is a lot. But there is a plus. If you look here, you have different signal counts. So this indicates the maximum number of counts per beam that you have. And even when you have a maximum 5 counts per beam, including accidental counts, where you have some intensity, your phase is perfectly reconstructed. When you have no intensity, not, but that is because it's not magic, you know, there are limits. And the limit is that when you have intensity, even it's very, very, very low, like 5 counts, which is super achievable, then you can reconstruct it. Of course, the price you pay is you have to do this 64 times, but it's a very quick measurement instead of doing a long one. So if your system is not stable, then this helps you. Okay, so I think we did, this was all. The results I presented were in a collaboration between my group and Marcos. These are our students who took part in this, and this is Ian, who helped us with the spider part, and Luis and Yongxia for the compressive tomography. Thank you very much.